Introducing Maxim's new EE-Sim OASIS tool, our offline analog simulator, including SIMPLIS. With OASIS, quickly, accurately, and thoroughly vet your switch mode converter designs. OASIS provides a smooth path to a working design, prevents unpleasant surprises later in your design cycle, and OASIS provides excellent self-support resources, including extensive tutorials. OASIS is an extension to our online EE-Sim and an enhanced upgrade to the offline EE-Sim SE simulation engines. OASIS includes over 150 SIMPLIS schematics for Maxim converters and allows you to download up-to-date schematics directly from Maxim's OASIS webpage. SIMPLIS schematics are also available for some Maxim parts with no online EE-Sim model. OASIS has the same online EE-Sim functionality. You can create and then download SIMPLIS schematics directly into the OASIS tool. That said, let's get started. So we are going to launch OASIS. And here we are in the welcome page. We're going to dive into the application schematics and open a converter schematic for the MAX 16 line 03. So now we see a complete schematic and we simply run that schematic. And we can see time domain waveforms and Bodhi plot waveforms. Okay, so, and let me re-emphasize the point. The big differentiator between SIMPLIS and SPICE is that SIMPLIS actually runs the time domain waveforms faster and gets you the Bodhi plot, the AC loop waveforms, basically in the same session as we've just demonstrated here. Okay, so the next step here is actually to make these waveforms just a little easier to view, in which case we're going to go up and undock that and reposition that. So now we can take a better look at the Bodhi plot waveform and the time domain transient response waveform. Okay, so we got some key OASIS messages. You use the OASIS simulator when your needs might exceed the conservative boundaries of our EE-Sim online tool. You get to quickly run both time domain and frequency domain simulations. SIMPLIS is industry's best switch mode power converter simulator. And with a one-time download, you eliminate the server latency and internet dependency of cloud-based simulators. And SIMPLIS is fast. You can reduce your simulation time to minutes or seconds. It can be 4 times or as much as 50 times faster compared to SPICE. You can also use advanced simulation and waveform analysis techniques, such as inserting custom voltage probes and current probes. You can do parameter stepping, Monte Carlo analysis, advanced Bodhi plots, and Fourier analysis. So how does OASIS work, and what is the best way to use the OASIS tool for DC to DC converters? Well, you start with a completed schematic. It's really important. Much easier and faster to start with a working circuit. The input voltage source and the load, the current source, come already configured. You get your simulation settings, your transient, your AC analysis, your periodic operating point. Those are all set for you. The components with initial conditions have those already set. For example, here's the initial condition on an output cap. Those are already set and you get your results immediately. So start with a working circuit and simply run it, and you can see the transient response. You can see the Bodhi plot. Very important. So where does this schematic come from? Well, we've already demonstrated downloading or loading the schematic from the local directory. Later we'll show going to the Maxim web page, and if we have time, we'll also show how to get the schematic out of EE-Sim. So we've already, one of the important things to do is to make waveforms easier to manage, okay? And so we got to do a little housekeeping. So under the File menu, we're going to go to Options, we're going to go to General, this Graph Probe Data Analysis, and we're going to readjust the graph placement. Overlay is the best approach to use when you're looking at a single monitor or doing a webinar. So that's where we're going to spend the rest of our time today in that mode. Okay. So why SIMPLIS and not SPICE? Why is SIMPLIS the best simulator choice for switch mode power conversions? Well, it comes down to time, speed. For switching converters, you get your answers faster. Load step, line transient, steady state. SIMPLIS is simply much faster. It has a unique mode, the periodic operating point or POP analysis, that quickly settles a simulation into equilibrium before you begin your transient time domain. And it sets up the AC analysis, the Bode plot solver algorithm. SPICE takes much longer and may actually not converge at all. In fact, let's take a look at SPICE tends to obsess about the edges in switching converter waveforms. SIMPLIS simply processes the edges and remembers so that it doesn't have to solve the same problem over and over again. SIMPLIS stands for the simulation of piecewise linear systems. It's a circuit simulator that was specifically designed to handle switching power systems. SPICE, on the other hand, was developed with integrated circuit emphasis at the transistor level. SIMPLIS is faster, avoids convergence issues, and achieves speed by modeling devices with a series of simple, piecewise linear straight line segments. It remembers and reuses the sequences to quickly handle repetitive equilibrium waveforms. SPICE tries to solve nonlinearities such as exponential expressions directly and does not always converge. So now we're going to clean this up a little. The other big advantage to SIMPLIS is the Bode plots are effectively built in. You solve the AC analysis directly from a POP time domain simulation, which is really effective for topologies that are difficult to analyze with average linearized small signal modeling. You can get Bode plots for loop gain and phase. You can get output impedance, PSRR, and you get this from the same model. The same model is used for both time domain and frequency domain in effectively the same simulation session. Very powerful. SPICE Bode plots require extraordinary extra time-consuming effort. Either you have to manually run long time domain simulations over and over with different stimuli, then stitch the results together manually, or create and correlate a second model, an averaged linearized frequency domain version of the time domain model. So to get Bode plots in SPICE really takes a lot more time. So back to the schematic. So we're going to spend a little time talking about the test equipment, the probes. We're going to talk about the source. We'll get to the source, we'll get to the load, but first we're going to talk about the Bode probe. Basic Bode probe. Very simple. You get to label the gain, you get to label the phase. You get to invert the phase if it turns out to be better for the Bode plot you're trying to measure. And then you can adjust the persistence of the waveform, which shows how many copies of the waveform you get to save with a new simulation. We really want to take advantage of a better Bode probe that SIMPLIS makes available. Okay, and that's shown here. In fact, let me demonstrate where to find that. So under this probe AC noise tab, you get this Bode probe with measurements. You get to place that there. And you get to specify some measurements. In this case, we would specify phase margin, gain crossover, and probably take off gain margin, okay, as an example. Let me dismiss that. We'll open this. So you get to change how the data is shown. You can have curves on a single grid or two grid. You can name the plot. You can name the caption. You can change the color. And you just end up with a better presentation of the Bode plot with the new probe. Okay. Some converters that are more complex can benefit from having multiple Bode probes. Let's dismiss that. And let's open up a. So here is a circuit, same circuit, except we have 3 Bode probes. Actually, it's not the same circuit. This is a more complex part. This is a part with external compensation. And because we have this comp node, we can actually measure the Bode subplots. That's very useful when doing analysis. So we'll simply run that. There's our Bode plot and our Bode subplots. So this is the total loop. This is the total loop, and here we've broken the loop into 2 halves, where we show the frequency response of the power path gain in blue, gain in phase of the power path. That's what you're compensating for. And then we also show the gain in the phase path in green for the compensating circuit. That's what you're compensating with. So by adjusting the compensation path or your power path, you get to tailor and optimize the overall Bode loop, Bode plot. And the payoff for doing a good job with the Bode plots is you end up with a good transient response. So we have some key concepts to keep in mind for setting up insightful time and frequency domain simulations. One, which I've just demonstrated, is to use Bode plots to optimize your transient response. Typically, you want your phase margin initially to be 50 to 60 degrees. If you have a buck converter, you want your gain crossover to be around 1/10 the switching frequency. For other converters, target 1/20th the switching frequency. For higher complexity converters, you want to break the loop into smaller Bode plots. We just demonstrated that. Another key concept is to set the initial conditions for all capacitors and inductors. So in this case, the output cap has an initial condition. That's real easy to set. You know the output voltage. The input voltage, input cap, is easy to set because you know the input voltage. Well, we have a capacitor on the bias pin. You can set that by looking up the data sheet. But what about the compensation? You got a capacitor in the compensation path, and it has an initial condition. You may be able to guess at it or get that from the data sheet. But if you download an existing schematic, you can actually refer to the values used on the downloaded schematics. And that's why it's powerful to start with a schematic from either the local directory or the web page. You get guidance on what these might be. So you also need to use the right POP settings, and we'll talk about that in just a minute. First, let's talk about setting up an AC loop, an AC analysis. So you open up this window, go to AC, and this is actually pretty simple. Start frequency, stop frequency, points per decade, whether you're going to sweep with a decade or a linear approach. But under select analysis, okay, you got some choices here. So we can actually turn all these off. You can ask for a POP analysis by itself. You can ask for a transient analysis by itself. You can start with a POP and then do a transient analysis. But if you ask for an AC analysis, then a POP analysis is required, okay? And POP will basically find equilibrium and set the simulation up for the AC analysis. So the simplest periodic operating point analysis quickly finds equilibrium, a steady state, on-off limit cycle of stable periodic switching systems. It saves simulation time, making it dramatically faster to complete your analysis and identify errors, and it makes AC analysis possible and immediately available on the same time domain switching circuit. Most measurements begin with and require systems in equilibrium. So if you get there quickly, you end up with a result faster. Once you're in equilibrium, the system can be disturbed and the resulting responses can be measured. So reducing the time to reach equilibrium dramatically improves your productivity. You get your results faster, or you can run more simulations in the same amount of time. So let's see what happens if you don't use the POP simulation. So here is a configuration where we are not going to ask for a POP simulation. Notice that we've taken out the Bode probes because you can't get a Bode plot when you have no POP solution. I'm going to simply run that and look at the output. So we're running a transient response. So here is our step load in the output transient response. So what's happening here? What's happening here is that the system did not start in equilibrium. It had to settle, okay? So you have control over the initial conditions on the components that you can see, but you have no control over the initial conditions within the Maxim IC. That's where POP can settle the initial conditions for all the components, both internal and external, so that you start in equilibrium. Without POP, you actually have to allow some time to elapse. You have to run the simulation longer to get to equilibrium before you can actually do your transient response. So that's an example of why POP is important. Let's go ahead and dismiss that. So here's an eye chart showing all the different settings that are available for POP. And this is part of a slide deck that will be available after this webinar. So we're not going to spend a lot of time on this, but I will demonstrate where these settings are. So under simulator, choose analysis, POP. This is the POP tab and the advanced tab. So you need to work with both. So in the pop tab, you want to set the maximum period. You've got to be aware of what the minimum frequency is in your circuit. And at the minimum frequency, that defines the maximum period. You want this to be at least 3 times the maximum period for pulse width modulation. For pulse frequency modulation, you want to go higher, maybe 10 times. Okay. The pop convergence parameter. This is an important parameter. It determines the accuracy that you achieve with each integration in the during a simulation. And 10p, or 10 to the minus 12, is a good trade-off number for switching converters. You want to, the iteration limits, both the cycles before launching pop and the iteration limit here, you want to start with 20 and no more than 200. And in pop, you want to show a small number of cycles once you've achieved equilibrium. 5 is our standard here at Maxim. So those are the pop settings, okay? And this is the periodic operating point strategy. The pop convergence should only be used for operation in equilibrium, okay, or steady state, where every cycle looks like every other cycle. This can be force frequency continuous mode, it can be discontinuous mode, it can be pulse frequency modulation if it's a true pulse frequency modulation where the frequency is a smooth function of load current. You can use pop for on-time converters, but only if you're doing 1 channel at a time, because 2 constant on-time converters will probably be operating at different frequencies. A reminder, AC loop requires a pop solution. You should use a pop basically to settle just about all simulations except startup, okay? And then if you have different modes of operation, for example, stepping from heavy load to light load, where light load you might actually be in a skip mode situation, you want to start your simulation with heavy load where you have equilibrium so you can get a pop solution. So when would you disable pop and expect no Bode plots or steady state analysis? That would be skip mode, minimum on-time operation, which is a way of triggering skip mode, hysteretic mode, multiple unsynchronized converters or constant on-time converters, bridge dropout, oscillating control loops. Any mode not operating in equilibrium are all modes where you would not ask for a pop solution. So let's talk about the voltage source. This is actually pretty easy to configure, okay? You have a start voltage and a pulse voltage, but if you're using this for a DC input, you simply set them to be the same. You want to set a delay time, you want to set a pulse width, then you also want to specify the rise and fall times, and these are important. To never set the rise and fall times to 0, which makes the rise times and fall times so fast, it could cause excessive and fictional current spikes in your simulation. It can cause your simulations to take a long time to settle, and in some cases can cause them to fail. You also want to set the source resistance to some number greater than 0. And one reason for that is if you're looking at the current in an input capacitor, well, if the source impedance had a zero value, then all the current would flow in the source impedance and you wouldn't get any current flow in the capacitor. So that current flow wouldn't measure anything. So those are the settings for the input source. Okay. Now, let's talk about the load. This is a load that actually was optimized for EE-Sim, and it turns out to be not the best way to load a circuit if all you're doing is looking at a SIMPLIS schematic. So we actually find it easier to replace the load with a static resistor and a place current source waveform generator, or place current source PWL source. Okay, So you might set the value of that load resistor to, in this case, 5 ohms. For a 5-volt output, a 1 amp load current, 5 ohms would be the calculated resistor. And then the pulse generator, maybe give it a 5 amp step value. You can change the wave shape. We actually like using the pulse, a single pulse, where we set the period and we set the delay, set the rise, and set the fall time. Okay. Or you can use the piecewise linear current generator, where you simply put in the time and the current vertices of the shape of the current waveform that you want to load the circuit with. Okay, and I'm going to dismiss that. And here we have a circuit that's already been populated with the new and improved pulse generator strategy. So there we have the step from 1 amp to 1.5 amps in the transient response. And I'm going to dismiss that. We also have to set up the transient time domain simulation. And this is pretty easy. You simply set the stop time. You can actually blank the first part by setting a time here. For example, if I were to put a millisecond here, then I would not take data for the first millisecond. And that might be useful, for example, if you're not using POP. It allows you to ignore the settling behavior at the beginning before you reach equilibrium. That would be useful for simulations where you're not using POP, or you're kind of forced to do that when you're using SPICE. Okay. Now, one of the important things to do is to frame your simulations. To set the times to are such that you minimize the length of the time that you need to simulate. So here's an example where we have minimized the delay time, we've minimized the pulse width, and minimized the stop time so that we show pretty much only the parts of the waveform that we need to see. We don't spend a lot of time grinding out static or equilibrium waveforms. So by paying attention, and here's an example that's not well framed. Okay, so this is a waveform where the width is wider than it needs to be. Okay, so we could have actually, by changing the pulse width and also the stop time, run a shorter simulation. So to properly frame the simulations, you would change the delay time, you would change the pulse width, come back up here to the simulator window and change the stop time. Okay, final reminder, you can select all these analyses and run them in one session and get the transient response and the Bodie plot. That's something that, that you cannot do using the SPICE simulators. That's something that is a SIMPLIS improvement and enhancement, a real differentiator compared to SIMPLIS and SPICE. So what else can you do? One of the most important simulations to run is a parameter sweep. And let me run this to generate the waveforms. Oh, that's right. I do this every time. For a multiple, you don't run, you actually simulate, you run multi-step. Sorry about that. So what's going to happen is we're going to change the output capacitor value. And we're going to run 3 different passes, each with a different output capacitor value. So that's the result of the first pass. And now you can see the second pass filling in. And now you see the third pass filling in the transient response. Okay, so you can see how the transient response changed as a function of the 3 different output caps. You can also see how the Bode plot, gain and phase, changed with a function of the output capacitor. And if you have the subplots going, you can take a look at the power path. In this case, the traces in blue, how the power path changed. Now, obviously, the comp path components have not been changed, and so there's no difference in the comp path. Now you can decide what your best choice is for the output cap, and then consider maybe redoing the compensation path. So now to set that up, very simple. Instead of a value for the capacitance, you use a parameter, in this case, C out, encased in curly braces. Okay. And then under setup multi-step, there's the parameter, no curly braces. And then in this case, we defined a list of 3 different capacitor types to run through the simulation. So that's the multi-step. Okay, so we've looked at a lot of features, okay, but we have to actually talk a little about some of the nuts and bolts, like how do you get started? Let's dismiss, okay, and go to Max's website. You go to the design page, the design tools, and you can see this is where you go to find the simplest models, okay? And this is where you go to find the OASIS simulator. So you simply visit this page and download the OASIS simulator. It's a very, very simple download, okay? Now for the SPICE, for the simplest models, okay? Simply visit the page. And once it populates, you can pick your model and just simply do a download. And I'll save that file. And then get back out of the web. And you want to load that file into a clean directory. Now, I happen to have a clean directory, which I point to in the file view here, and there's nothing in it. So off screen, I'm going to load the zip file into that directory and unzip. time to do its thing. And now here's the schematic that has come from the website. And I can simply open that. And let's take a look at that. I'm going to zoom out. And it has a lot of extra information. Okay, so here's the schematic we want to simulate. But we also have a lot of notes. Okay, we have some notes that explain the different modes of operation. We have the notes that explain how to set the initial condition for the different components. And then we have the notes which explain how to set up the different sources and how to set the pop parameters. This is one of the reasons why it's important to start with a schematic from the web, because it has a lot of information that helps you get that first simulator working. Okay, so let's zoom back out. And then when you don't need them anymore, you can simply dismiss them and get back to and run. Okay. So that is downloading the schematic from the web. Now, I've been using the file viewer quite a bit because I have actually a lot of schematics to share with you, and this helps me organize them and get to them quickly. So it's actually important to add directories when you're working on different circuits. But behind the file view, we actually have two other views. We have a part selector, okay? And the part selector allows you to place components. I'll talk a little more about that. And then you get the command shell, where this is where you get error messages, okay? For example, if we were to make a mistake in the schematic, and I have an error message off camera. So here's the error message. When you dismiss the error message, you're going to see the result over here. Okay, so this will give you the error messages in your session. Oops, that. Dismiss that. Okay, and back to file view. And go back to the OASIS schematics have two icons that help you in your design process. The first gets you to the product information page. So simply poke the icon and it gets you to the landing page for the Maxim part on our website. Here's where you find the data sheet, eval kit, any other collateral involving that Maxim device. The other icon takes you directly to EE-Sim and puts you in the design requirements page for that device. So you can actually update your design requirements like output voltage, and then create your schematic and download that new schematic directly into the OASIS tool. The first one will take you to the product page for that device. So any information that's available for that Maxim device can be found on the product page. I'm waiting for it to render. My login is stale, so I had to redo the login. Oh, I don't like the way that's going. Okay, so that was supposed to open up in the I logged in too early and my login expired. This other tool will take you to EE-Sim and it will populate the the EE-Sim Online Design Tool. I'll demonstrate that later in the session if I have time. Support is available on the welcome page in this EE-Sim support section. This is the tutorial, and then you can always contact Maxim support. So we got some nuts and bolts in the schematic. Copying components, kind of like Word. You can do a right-click copy. You can do paste. You can do a select, edit, copy, paste. You can do Control-C, edit, paste. Okay, so it's all very straightforward to do copying a component. Placing a new component, you can place from the tab, or you can actually place from the part selector. All very straightforward. Wiring. Wiring is fairly straightforward. If you take your cursor and hover it over a terminal on a connector, it changes to a pin, and you can edit, and then actually you can undo, 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 undo. When you're wiring the schematic, we try to avoid doing this. That's what we call a dot cross, okay? And one of the reasons is it may not be clear if those are connected if you zoom too far or look at the schematic on a device that has a really small screen. So what we try to do is fix that by using only T intersections. And then also we try to draw our schematics to eliminate extra elbows, because it just makes the schematic a little more difficult to follow if you have these extra elbows. And the way to fix that is to simply drag and, let's see if I can. Okay, so wiring is pretty straightforward. We talked about the nodes. Maxim device. Some Maxim devices, in fact, almost all, require some configuration. If you double click and edit the part, you open up a GUI, okay, that gives you control over the parameters that we expect you to need control over. You can also do the edit, add properties, and this gives you a lot more control. There's a lot more things to change. But unless we give you guidance on what to change, this is also really dangerous too. And this is mainly for advanced users or users with more information. So for most people, I would restrict yourselves to using just what's available in the GUI for that part. Okay. Now, it's important to customize the SIMPLIS environment to work efficiently. Configure the viewer window, name and group your waveforms, and this is useful pasting in measured data directly to correlate with simulations. Okay, so we've already configured the window once. Let's go ahead and show you the other. So we're in this graph placement. Okay, new window is important when you're using multiple monitors. Okay, let's see if we still have a working simulation here. And so you get this view of the waveforms. Wait for it to settle. Now notice I see the schematic, but I don't see the tab for the waveforms. But if I roll over this icon here, there's the schematic and there's the waveforms. Well, now I see the waveforms but I don't see in the caption, I don't see the schematic. So you have to hover over the icon here to get back between the, but what's useful about this is you can take this and move it onto your other monitor. So here I'm half on one, I'm half on the other. I'm completely off page, and I can open my waveforms on one monitor, my schematic on the other. And this is how I work during the day when I'm in my cube and I'm not on a webinar. Okay, but because of the webinar, I actually need to dismiss that, and I need to put it back. So File, Options, General, Graph Probe Data, Overlay. Okay, renaming the waveform tabs. Okay. Sometimes you'll get a schematic and you run the and take a look at the tabs, the captions down here. They're all kind of cryptic. Okay, it's kind of hard to figure out which one's the output, which one is the switching. It's just not very clear. Okay, so to fix that, you simply open. So when you open the probe, edit probe, you get a chance to name the graph. Okay, in this case, we've named the graph for this probe output, but you have to set this tab caption to name. Set that checkbox. Okay. So now we're going to rerun that. And the output caption, you can see, now has the new name. The others are still cryptic. Okay. And, but if you go to the trouble to dismiss that, only name, now you can see the tabs are all have names that we have cited for ourselves. Notice we had to replace the Bodhi probe so that we can name the Bodhi probe output. Okay. Copying and pasting data. Okay, this is really powerful because you want to be able to compare your measured results with your lab results. And I'm just going to show a quick example of that. Dismiss. And here is the plot. Blue is actually the measured data, and the red is the simulated data. And so in this case, you can see, well, we did a pretty good job matching the sag peak to peak, and the timing looks really, really good. We're a little off on the step down, but quite frankly, this is the important one. So this is an example of what I would call a well-correlated simulated response to what happened in the lab. Okay. So we will close that, and so we've already demonstrated the zoom. You can do a control and a mouse scroll and work your way in and out. You zoom in, you get the scroll bars, kind of like Windows. You can center yourself. You can use and you can also partially zoom and then go back. So it's all very straightforward. Showing and hiding waveforms. Generate some waveforms, and so now let's say I want to take this blue waveform, select the waveform, And we have these eyeball icons up in the taskbar, and you can simply tell I want to hide or I want to show. You want to be able to zoom in, simply draw a box, and you can zoom in. Cursors toggle on, and now you have the control over the cursors. And SIMPLIS has a interesting way to migrate the cursor from one waveform to the next. See this cross point? You roll over it and you see the icon change. Okay, once that icon is changed, you can grab that and move it to the other window. Okay, and then you can use these controls to get yourself zoomed back. So that would be the cursor control. You can get a lot of data in a waveform, and sometimes it's daunting to analyze. So we're going to close that. Close that. Simulate. If you have a lot of waveforms that show up in the same window, you can stack all the curves, and it simply creates a new grid per waveform. Okay. You can also move the waveforms around. You can create grids. You can create axes. In this case, I'm going to move this current waveform back down to this current grid, and you simply do that by selecting the grid that you are migrating to, selecting the waveform and curve. Curve. Okay, so let's do it again. You want to select the axes. You want to select this and curve, move. Okay, so now we're both on the same. And we want to recruit that. Okay, well, what if we want to put the currents back on this grid? We want to add a new axis. So we select axes, new axes, and then we want to migrate these curves back to the second axis. We select the curves and move the selected curves. So now we basically rebuild it back to the way we had that. So that is creating axes or moving waveforms around. Okay. I have one advanced topic to. Okay, should we go to Q&A? Okay, I'll skip the output impedance topic unless somebody asks me a question. So how do we get started with this Q&A?
Do you see at the bottom of the screen, Brooks?
I see. I don't see anything just yet. Sure.
Want me to read it to you, or?
Yeah.
Sure. Okay. So first question is, actually we've answered that one. How does your software compare to LT SPICE? You answered that one already, so I'll skip that one.
Better. I used to work for LT. That should answer your question.
So let's see. Myron Steinberg asked, dissipated power / efficiency / temperature on the IC? Question. We
actually go to a lot of trouble in our EE-Sim online design tool. Okay, and so we have not focused on that for SIMPLIS. So we would ask you to take a look at EE-Sim.
Cool.
Okay.
He then asks, is it possible to simulate power controllers with external MOSFETs, and how to change or use different models of MOSFETs?
We can use external MOSFETs, but the MOSFET models for SIMPLIS are actually simple representations. Okay, it's difficult to import a SPICE model into SIMPLIS. But if you really want to simulate the MOSFET, it actually is worth your while to put it in a simpler simulation that targets the switching waveforms themselves. And it might actually be easier to do it in SIMetrix, okay, which is part of our OASIS tool. So I'd be happy to go into more detail offline on that question.
Great. And then from Myron, is it possible to simulate ICs from different companies?
Why would you want to use a different company? Well, the easy answer to that is if they have a SIMPLIS model and you have a license, that would be how you would simulate for different companies. But you cannot expect an LT-SPICE model or a P-SPICE model to import into SIMPLIS. Also, OASIS does require that you're using Maxim devices. They're encrypted and keyed. And when you download a Maxim schematic, the OASIS environment reads the key for that Maxim device and opens up the topology count to allow you to simulate that Maxim device. So.
Great. Okay, so Shay Ludan asks, can EE-Sim OASIS work with other manufacturer components? Oh, yeah.
Well, not power management. No, it's targeted completely on Maxim power management parts.
Okay, anonymous question. Do the inductor models capture saturation effects?
No, we do not capture saturation effects. It is possible to do that, but we do not do that in the models that you can download today. But I can take that question offline on how to implement saturating inductors, because there is a way of using SIMPLIS that allows you to implement piecewise linear models for your inductors and your capacitors. That's above the scope of our discussion.
Okay. Benjamin Bacon says, I really like the working environment interface. What are the minimum requirements for running the software?
Not a Mac. It in this day and age, SIMPLIS pretty much runs on anybody's PC. But if you have a Mac, then you have to have a pretty strong Windows emulation. So I think Mac users are at a bit of a disadvantage. But this should run on any Windows machine. I would encourage you not to try to run it on like a phone or a Surface. Okay. You just run it on a full laptop or a desktop.
And Reverend Fuzzy had asked in chat earlier, is there a Linux version?
No, we do not have a Linux version.
Okay. So Jim Paul asks, regarding the differences you pointed out between simulated and measured, are the differences mainly due to the parametrics of the simulated components set to different values than those of the actual part, or differences in rising of their waveforms?
It always comes down to a complexity argument in the model. For example, if you're trying to correlate a Bode plot, then you really need to know the gain of your air amplifier. And that can be a little tricky if it's not specified by the vendor, or if you have internal compensation components, because they're going to vary quite a bit if they're integrated. But if you put the time into the model, then you can expect the correlation between the lab and the bench to be really, really good.
Okay, so that's all for now. I guess, anyone else have any last minute questions, or is that it?
Do I have time for 2 more slides?
Sure, we have, yeah.
Okay, because I really wanted to show the output impedance slide. So output impedance for a converter, in this case, black is the measured output impedance. It's also, this is the closed loop output impedance, the red being what we call the open loop output impedance. And let me kind of explain where that came from. So here is a schematic. It's a converter, okay? And we've removed the loop Bode probe. In fact, we've repositioned it up here and turned that into an output impedance probe. So you drive the output of the converter with a current source, okay? And the output voltage is going to move around. And by plotting the effective ratio of the voltage to the current, you plot the output impedance directly. And to do that, we had to convert the current to a voltage, so that's what this little block does. So this is the closed loop output impedance. Open loop output impedance is pretty much due to the output capacitor, the inductor, the sense resistor. And so if you simply copy and paste it down here, add another probe, you can run the simulation all at the same time and compare them, okay? And so this is the closed loop output impedance, the open loop output impedance. And notice out here at this frequency, they merge and they become one. Now, why is this important? When a user of a converter wants to influence the output impedance, okay, this tells them what they can do with the control loop. Okay, you can change the output impedance down here by messing with the Bode plots. Okay, but above a frequency, all you can do is change the output capacitor and change the layout. Okay, so it helps guide you to where you have to spend your effort when you want to optimize the output impedance of a power distribution rail, for example. And it's very easy to do this type of analysis using SIMPLIS. So that's the one advanced topic. The only thing that I didn't get around to talking about today is the interaction between OASIS and EE-Sim. EE-Sim is the online tool. With EE-Sim, we have limits on the kinds of simulations that you can do, and we have limitations on the changes you can make to the circuit, and so it's actually very carefully controlled. But when you download into OASIS, you get to do pretty much whatever you want. You get to play with fire. So. Anything else?
Looks like we have one more question.
Sure.
Are IC tolerances considered taken into account as e.g. best worst case IC models?
Excellent question. And remember I was talking about the GUI? The GUI for a part. This is a MAX 20098. This is a part that was designed for the automotive environment, and they ask that question a lot. And if you open up this GUI, you see you get this main tab where you get to change the part number, you get to change the switching frequency. but you also get this WCA. That's a worst case analysis tab. And for that, you actually get to schmoo, or change, the transconductance of the air amplifier to plus or minus 6 sigma, or the current sense resistor plus or minus 6 sigma. These were judged to be the parameters that the user may most want to schmoo. Okay, not all Maxim parts have this capability, but it's actually very straightforward to build this into any SIMPLIS model. And so if the broadly available model doesn't support this, okay, for larger accounts, we could actually arrange this. But that would be kind of a custom path. You'd have to work with the field application engineer. Good question.
Okay, and one more because we're getting really over time. Benjamin Bacon asks, do SPICE models port into SIMPLIS or vice versa?
They do not port well into SIMPLIS. They port better into SIMETRIX. Okay. We do have our some arrangements with third parties that will take a SPICE model and create a SIMPLIS model. But then again, it's also a question of what behavior you're trying to measure, which will guide the complexity of the model. Now, we haven't spent much time talking about SIMETRIX, which is a SPICE, a really good SPICE simulator. But in some cases, it might actually be better to use the SIMETRIX capability of OASIS. We haven't focused on that yet, but we're going to. Mainly our op-amp product portfolio is going to drive our SIMETRIX side of OASIS. I wonder if that answered that question.
Well, I guess Ben is it possible for Ben to contact you later if he has more questions on that?
Sure.
Is it best to contact you on?
Send me an email.
Okay. And that will be in the presentation when we send it out?
I can arrange contact information in the presentation. Erin?
Yeah, there's a link at the bottom of the online tool that you can reach us on.
Oh, okay. There's a generic link in the online tool.
Well, it comes to 3 of us, so
okay.
You'll see it.
Great. All right, everyone. Thank you all. Thank you so much for giving this talk, Brooks. It was great. And thanks everyone for coming.
Thank you.
Yeah. Have a great rest of your day. All right, everyone. Bye.
Bye-bye.